On our Canvas page, in the web links section, is a video by Numberphile called Beautiful Trigonometry. I know that sounds like an oxymoron, a contradiction in terms, but there is a deep connection between the trig functions we want to work with and the circle. And what I want to do is I want to take our unit circle ideas and extend our process so that we can use function ideas, the algebra ideas, to talk about trig. So our current starting point, remember, was the circle. And we take any number we want. Any number. And turn that number into an angle in standard position by wrapping it onto the circle. So we start here at this point, and we go counterclockwise around the circle, laying out a piece of string whose length is t. Let's suppose we end up here. This angle is t radians. But this is also some point, P, on the unit circle. And since that circle is a unit, I drop in a little right triangle in my head and I say, oh, that x and y now has a hypotenuse of 1. All of my trig terms can be defined based on this point. Did this with cosine and sine, being the x and y parts of that point. Well, let's take the same ratios the rest of the way. So tangent is now y over x. And secant is now 1 over x. And cosecant is 1 over y. And cotangent is x over y. But in order for this to work, for these two, I can't divide by 0. So that's only defined when y is not 0. And for these two, I have to make the same claim about x. But now, I can forget triangles exist. Strictly think of this on the circle. To that end, the video I'm talking about on Numberphile calls trig functions circular functions. And I want to think of them that way moving forward. Now I can still use all the reference information I have. I can still use the information I got from the triangle because that's still applicable here. Even if I don't know the value of t that gives me the point in question. So, for example, if I tell you up front the value of t is 2 pi over 3, then from our pictures on the unit circle, we know where that angle is, and we know what reference it has, and we know what point it terminates at. So, what quadrant is that in? Quadrant 2. I did put up a scan of a blank unit circle that you could download, play with, do whatever you want with. So that's in quadrant 2. What's its reference? The cosine and sine numbers, the x and y, that go with that are
-1 over 2 and square root of 3.
and we know that the x is negative because we're in the second quadrant. If you were looking at the reference numbers, you'd have 1/2 and root 3 over 2. But now that means I've got an x and a y, which means I have all the rest of my trig functions. I can actually think of this and generate this list from knowing just those two numbers. From knowing cosine and sine. I get the rest of it. Here is where it is up to you to choose how far to simplify. I'm going to write the tangent, that's sine over cosine, y over x, root 3 over 2 over negative 1/2. The over 2's cancel. So I would simplify. Is it a requirement? No. Is it easier to work with the square root of 3 than this mixed fraction? I think so. Now I can take reciprocals. Secant is 1 over negative 1/2. Well, that's negative 2. Cosecant, 1 over y. 1 over root 3 over 2. That's 2 over root 3. You could make it 2 root 3 over 3. That's perfectly fine. I don't see a need to rationalize the denominator as much. Again, your choice. Cotangent. Cotangent is 1 over tangent. Again, you could rationalize. Up to you. But what that means is that now, as long as I know what's going on with my reference numbers, I get the rest of it. Even if I don't know the t. Dan, you're looking at me like you're confused about something.
Yeah, cotangent. Yeah, 2.
Okay. So I did that as 1 over tangent because x over y is 1 over, but I could also do it as x over y. Right? And then the over halves cancel when I take that out and flip it over.
Yeah, then you multiply it by root 3.
Oh, yeah, absolutely.
And then that equals root 3 over 3.
Yes, but it's negative.
Right.
Yes, you could, but that's like this one. I don't require that you rationalize the denominator. That's certainly acceptable, but I don't require it. More questions?
When you graph the 2 pi over 2, what's the closest angle to the horizontal?
That's our reference angle. That's 1 pi over 3. So t itself is here. And then this is TR, And that's the rest of a straight line. The rest of a straight line, pi minus 2 pi over 3 is 1 pi over 3. If I went 2/3 the way across, I got to go the last 1/3 to finish it. Please notice, I have absolutely no idea what t value gives me these numbers. These numbers are not on my table of known reference values. So I don't know what the angle is. I'm okay with that. Is this point on my circle? Easiest way to check is to see if it obeys the equation for the circle. So I square my numbers. -7 over 25 squared plus -24 over 25 squared gives me 49 over 625 plus 576 over 625, which is 1. So this is a point on my circle, which means these are the cosine and sine for something. I just don't know what that something is. Where is this point? Quadrant 3, which means I could draw it in spite of not knowing what the angle is, -7, -24. So it's going to look like this for my point P. So I don't know what this angle is. We could call it anything you want. But if I give it a name, then I can use that name to do the sine, the cosine, and all the rest of them. So what do you want to call this angle? Theta. So then I can say cosine of theta, sine of theta, tangent of theta, secant of theta, cosecant of theta, and cotangent of theta. And because you know cosine is x and sine is y, you know all the rest of them. Tangent is y over x. The over 25 part will cancel out. And then secant's 1 over x, that's 1 over cosine, so I flip this one over. Cosecant is 1 over y, so I flip this one over. And cotangent is x over y, but it's also 1 over tangent, so I can just flip this one over. At this point, I am reminded, hey, look, in the first 3, tangent is positive. We were in the 3rd quadrant. Does that match what I think should happen with being in the 3rd quadrant? David, why were you nodding? Why do you think the answer is yes there? Aha, we had that thing about which ones were positive, which ones were negative. A, all, S, sine is positive. T, tangent is positive, the others are negative. C, cosine is positive. So this does match, and that means, again, the same statement I made on Tuesday still holds. If I know what's going on in the first quadrant, I know what's going on in the rest of them, simply by adjusting for plus and minus. I also told you about the hand trick, right? Down here at the bottom of page 512 is their version of the table for the hand trick. Notice 0 through 4 for sine, 4 through 0 for cosine. But I think this table's upside down because the angles are going bigger as we go down, not bigger as we go up. But that's me. I think that's helpful. It helps me remember what's going on, and it helps me to figure it out. Questions? Okay, but now I have a new piece to this. If I'm thinking of these as functions of t, I go back to last semester and I say a function has a domain and a range, an input and an output. It's got a set of numbers that are allowed in. And we did a bunch of algebra properties last semester. Some of them were easy to remember and some of them sucked. So let's start with the easy, I hope, things. For the moment, I want to think of these two as separate functions. So I'll call the sine one the f of t, and I'll call the cosine one g of t. Now, based on the circle picture I started with, back here, no matter what number I pick for t, we're going to get a point on the circle, right? No matter what t value I end up at, that line, that ray is going to cross the circle somewhere. And that means that no matter what t value I put in, these are both defined. And that means that their domain is any number you want. Now, math geeks are weird. We have a different symbol for this set. This is the set of all real numbers. The symbol I use for the set of all real numbers is a hollowed out looking capital R. So that symbol will come up fairly frequently for us. Okay. What comes out of these functions? What set of numbers are the outputs, cosine and sine? Remember that I'm going to get a point on my circle.
Between -1 and 1.
Between -1 and 1. Because the lowest point on my circle, that would be the smallest possible y value, is at -1. The highest point on my circle, that would be the biggest possible y value. Similarly, the leftmost x value is -1. and the rightmost x value is plus 1. So for both of these, I can say that the range goes from -1 to 1. I vaguely remember this idea from algebra. It was a long time ago. Or it was more recent and it didn't stick and I'm still trying to reprocess it. That's okay. What's allowed in, what comes out. Well, that's 2 of the 6. Let's group the other 2 the way I did on that first page. Tangent and secant were grouped together because both of them had x's on the bottom. If I think of these as functions, they're functions involving division. Where does division F stuff up? Or where does division get messed up?
Number 0.
Any number 0?
Any number over 0.
Any number over 0. And since the bottom here is an x, whenever x is 0, I can't do this. But x goes with which of these 2 trig functions? Cosine. Oh, let me look back at my circle for a second. What points on this circle have x equal to 0? Yes?
0, 1, 0.
And that's up here and down here. 0, -1, 0, 1. So those are the 2 points that are going to give me places that I can't plug in the tangent or secant. What angles, what t values land at the point 0, 1? Say again? Pi over 2. But that's not the only one, right? Wait a minute. Pi over 2 is going to put me up here. Negative pi over 2 is going to put me down here because I start from there. But that's still not the only one. As a matter of fact, there are lots and lots and lots of t values that will screw this up because I can go around the circle as many times as I want, right? So in addition to t equals pi over 2, if I want to land, I could go all the way around the circle and then stop there, right? What kind of an angle is that? We gave that a name. An adjective, a something angle. It ends at the same place. Co-terminal. So I could give you any co-terminal angle. And a co-terminal angle is different by exactly 2 pi. So I add 4 pi over 2. But I could also subtract. Instead of going clockwise, counterclockwise, I could go clockwise. I could go around the circle the other way. So if I subtract pi's over 2 pi's, I could get minus 3 pi over 2, or minus 7 pi over 2, or minus 11 pi over 2. All of these end at 0, 1 as our point. Which means all of them, all of those t-values break tangent. They break secant. On my table, on my unit circle, those are places where those two functions are undefined. But wait, there's more. Because all of those two infinite lists all ended up here. What about the ones that end down here at 0, -1? I'm going to do the same process, but I'm going to start from this. Notice that if I subtract I get the same numbers as in that top list, but they're negative. If I add 4 pi over 2, I get the same numbers as in this list, but they're all positive. So here's a question for you, so that I could actually write my domain nicely. How can I describe this collection of values in a simpler way? I could do any of those, yes, absolutely. But I really don't want to try and list out all those different pieces, because if you think about it, these numbers actually mix with each other, right? Think about the number line. Here's 0, here's pi over 2, here's minus pi over 2, but then instead of adding 4 pi over 2, what if I only added 2 pi? Then I get this one, and then this one, and then this one. See how I'm bouncing back and forth between these? And if I go this way, the same thing happens in the other order. So if I tried to list these as brackets, I would have to list this section, and this section, and this section. And that's a lot of unioning, isn't it? Because each of those has to get listed separately. But the other way I could do is I could say it's everything except these. Like they were little open circles. Oh, not this one. That one's okay. This one, this one, this one, this one. Like they're all little open circles that we're not allowed to use, right? Those are the F-up points. Throw them out. So I would like a description of all of these points. What do they all have in common? They're all pi over 2 times something. But there's even more something special about what we're multiplying the pi over 2 by. Multiplying pi over 2 by something that's always odd. 1, 3, 5, 7, minus 1, minus 3, minus 5, minus 7. I didn't do 2 pi over 2. I didn't do 6 pi over 2. I only did the odd ones. So I can say that the domain is everything except odd multiples of pi over 2. And that prevents me from writing it as a union. I can just say, hey, take those numbers and throw them out. Now, I could write this symbolically, but I must tell you, writing this symbolically is a pain in the neck. So I'm simply going to say, oh, all the numbers except, I want you to take away, subtract out, odd pi over 2. And I actually do it in words. I write the word odd in there. Our textbook was written by math geeks who are less communicative. They are annoying. Okay, so now I need to ask a really stupid question. How do you know when a number's odd? Okay, but how do you know when a number's even? Damn it, that's a circular argument. And I like circles, but it's not going to help me here.
I can't remember exactly.
It's not the next one.
I keep skipping. I like this. I need a test. It isn't divisible by 2. So a number that's even divides by 2. A number that's odd doesn't, and has a very particular remainder. If I divide it by 2, the remainder should be, that would be the decimals. Remainders are always whole numbers. It's a multiple of 2 with 1 left over, right? So the remainder is always 1. So unfortunately, a math geek would say, if I want to guarantee that a number is odd, I should write it as an even number with 1 left over. So you'll often see this, where k is an integer, a whole number, either positive or negative. And then if k is 0, I get this one. And if k is 5, I get 11 pi over 2, which was one of our throw-out numbers from off the list, right? If k is negative 6, I get negative 11 pi over 2. So this is another way of writing odd pi over 2. Personally, this is a little more geeky than I want to get with you all. The reason for breaking up even and odd numbers, like Dominic suggested, is to figure it out exactly that way, to write everything as symbolically as possible. That's more confusion than it's worth, in my opinion. But you'll see that in the textbook. I didn't want it to break you. I'm perfectly happy with this. Throw out the odd pi over 2. But that's exactly what this says as well. Whew. One more geeky note. Just like there's a funky symbol for all the numbers, there's a funky symbol for integers that comes from the paper that discussed the set of integers, which was in German. And the set of integers is the Zahlen. So the integers get a funky looking Z. If you never see that symbol again, I'm perfectly happy with that. If you never use that symbol, that's fine. You won't need it until you take discrete math if you're going to. And if you're not, F it. Don't worry about it. Okay. Questions? Thinking about the domain only means I forgot something. Function has a domain, it also has a range. Because we're dividing, ranges are a little weird. When I do the range of a tangent, that's y over x, right? And as we talked about on the circle on Tuesday, I could make x really small and y really big. Or I could make x really big and y really small. So I could get really small numbers out of tangent. I get really big numbers out of tangent. I get really negative numbers out of tangent. Out of a tangent, I can get a range of anything. So the tangent's output can be any number. You can. Which one? Tangent of t has range r. So, okay, I'll rewrite that word. And that was because it's y over x, right? But secant is 1 over x. And cosine was always between -1 and 1. If you pick a number between -1 and 1 that isn't 0, and do 1 over that number, what do you get? Do it on your calculator right now. Pick a number between -1 and 1 that isn't 0.
You said divide by one?
Yeah, do 1 divided by it. There's even a button for that on your calculator. You can use the x to the -1 button, because that means 1 over x. Blaze, what number did you pick?
0.8956.
And when you flipped it over, you got
Number one.
a number bigger than 1. If you pick 0.2 and flip it over, you get 5. If you pick -0.3, you're going to get -3.33333. If you picked 1, you'd get 1. If you picked -1, you'd get -1. But if you pick any number that's a little smaller than 1 when you flip it, your answer is bigger than 1. Wait a minute, we looked at a graph like this. So I'm off the bottom again. If I'm only looking where x is between -1 and 1, all of my y values for this graph are this way. Which means when you get stuff out of secant, you can never get a number between -1 and 1. You only get the numbers that are y values here on the bottom or here on the top. You never get the band in the middle. Whoa. Taking stuff between -1 and 1, I'm flipping it over. And flipping it over does this. It takes the stuff that's negative, makes it way negative, it takes the stuff that's positive, makes it way positive. 1 over x is a very violent function. Rips stuff apart. Most of the time, I am more concerned about the domain. I want to know where the function works and where it's broken. Both of these work and are broken at the same places. Their outputs are very different, but their input sets are the same. Questions? Sine, cosine, secant, tangent. I got two left, cosecant and cotangent. We had cotangent was x over y, and cosecant was 1 over y, which means I need y to not be 0. Wait a minute. Let's do the exact same thing we just did with x. Let's do it with y. Which trig function goes with y? Sine. Go back to my circle. Radius of this circle is 1. It's always my u. Which points have y value of 0? David, what did you say? Pi would be the angle that puts me over here, right? What angle puts me over here? Or 0, right? I can make the same sort of list. To end up here, I could use t equals 0, 2 pi. I could also go the other way. I could get negative 2 pi. I could get 4 pi or minus 4 pi. I could get 6 pi or minus 6 pi. And over here, I get pi by going this way. I get minus pi if I go that way. But I can now add 2 pi. So all of the places where I'm going to get a 0 in the y value are all whole number multiples of pi. And those are the spots we have to throw out. So I can say, hey, throw out any multiple of pi where n is an integer. So we had the half pi's that got thrown out before, and now we have the whole pi's that are getting thrown out this time. And this will be the domain for both cotangent and cosecant. And what we've really figured out is we figured out all the places where cosine is 0, and we figured out all the places where sine is 0. Sine is 0 at every whole number multiple of pi. Cosine is 0 at all the odd pi over 2's. The range for these is the same as the range in the previous part. So the range for cotangent is the same as the range for tangent. The range for cosecant is the same as the range for secant. But this now means that no matter what number you give me, it's got a cosine, it's got a sine, as long as I think of it as part of the circle, which means I'm thinking of it as a radian. And if it's not on my list, I can go right here. Because down here, I've got a sine button, I've got a cosine button, I've got a tangent button. And I don't care what number you give me. $2.75. Let's do the cosine of 2.75. Sold. Let's do the sine of 2.75. 2.75 is smaller than pi, because pi is a little bit bigger than 3. So that number is, if I think of it as an angle in radians, is in the second quadrant somewhere. Cosine should be negative, sine should be positive. Those should be a point on the circle. So if I take 0.924302378 and I square it, and I add 0.38166099921, and I square that, x squared plus y squared should give me 1. That's a point on my circle. And that means I can get the tangent of 2.75. We're in the second quadrant. Sine is positive, cosine and tangent are negative. How do I get secant? I'm looking at my buttons, I don't see a secant button. 1 over cosine. You want cosecant? 1 over sine. You want cotangent? 1 over tangent. I have all of my trig functions from just 3 of them. Really from just 2 of them, because I can get tangent from sine and cosine, but we use it often enough that we built it in. So if I don't actually know what the numbers should be, I can pull them out anyway. That means that these functions that we are describing got programmed in here so that no matter what angle you are giving me, no matter what point I'm trying to find on my circle, I have a method to do that. It turns out that for enough accuracy on the calculator, there are actually several very, very quick calculation methods to get sine and cosine and tangent that require just adding up powers of the number you give me. That's called a series, and we'll talk about it a bit in discrete math and a bit in Calc 2. Questions? There's a lot here.
What's the domain for cosecant and cotangent?
Take away all the whole number pi's. Other questions? When I did this one, that domain in particular, Dan, I kept running into a problem in my head. I kept saying, hey, look, it's broken at plus and minus pi. It's broken at 2 pi, plus and minus 3 pi. when I go around counterclockwise, getting the same thing as when I go clockwise. There's an algebra idea, again, about looking at an equation's properties for positive numbers versus negative numbers. This is a definition from a function, I think it's in chapter 2 of our textbook. What this says to me is something, I think we were talking about parabolas last semester when we talked about this. We looked at the graph of a parabola. We noticed that the graph of a parabola is the same on the left side as it is on the right side. When the x is negative, I get the same value as when the x is positive. What type of symmetry did we say this had? Y'all have the textbook. You don't have to memorize this. You can look in the book, in the index, look up symmetry and see where you can find it. Or the internet. I guarantee you we gave this a name. Look on the book. If your book is online, open up your book online. If your book is on paper, grab it, take a look. That's specific to parabolas. A parabola gives me a quadratic function. But any function that has this sort of left and right idea is symmetry.
F is a one-to-one function.
One-to-one means that I only get one output, one input for each output, right? And if I'm telling you that the y value on the left is the same as the y value on the right, then I've got two inputs that are giving me the same output. So unfortunately, that's not a one-to-one behavior. An inverse function undoes a function. It doesn't move, it doesn't deal with minus signs as much. Ooh. Oh, we're getting closer though. I did find it in the textbook. It's on page 241. If we have the same y value on the left as we do on the right, we call that an even function. If we have the opposite y value on the left than we do from the right, we call that an odd function. The idea about being one-to-one is about horizontal lines, so I can see where those would get connected. This is now another way I can think about the algebraic properties of a function. And again, I'm gonna go back and write this definition in our section so that I can start thinking about this. That word that should be in that blank is the word even. And then number 2, if f of minus x is the opposite of f of x, we say that f is an odd function. David, every quadratic has what highest power? Has what for a highest power? In order for me to use the quadratic formula, the equation has to look like ax squared, an even number. So we actually do get this property kind of from quadratics because we say, oh, it's got that evenness to it. I've got 6 functions: sine, cosine, tangent, secant, cosecant, and cotangent. Do any of them have either of these properties? Just looking at what we were looking a moment ago about the way in which sine worked and the way in which cosine worked as we go around the circle. If I switch x with minus x, that means instead of being in quadrant 1, I'm now in quadrant 2. Or instead of being in quadrant 4, I'm now in quadrant 3. If I change from quadrant 1 to quadrant 2, do my y values change? Do my x values change? Over here, my x value is positive. Over here, my x values are negative. But the height stays the same, yes? If I go and look at my functions, I want to switch t with minus t. What's going to happen to my x value when I change from t to minus t? I wish I knew which radiator that was. I would kick it. Give me that lovely high squeal. What happens to my x value? They both stay the same. Which function only deals with the x value? The way we wrote all the trig functions in terms of x and y, which ones only have x? Cosine. That means the cosine up here is the same as the cosine down here. That's even. And since secant was 1 over x, I can say the same thing about secant. On the other hand, y values up here are positive. Y values down here are negative. So if I think of the sine of minus t is the same number, but negative from the sine of t. That's exactly what my function being odd means. It turns out all four of the other trig functions have this odd property. So out of all six of my trig functions, only two of them are even. Cosine and secant. Everything else is odd. And that's an algebraic property. But on page 241, back in chapter 2, they were using it to describe graphs. And that means that I should be able to create graphs for these. And when I do that, I should be able to see these properties the way they showed up in the picture. Even means it should be the same on the left as it is on the right. Odd means it should be the opposite on the left that it is on the right. I'm not graphing yet, should be able to. On page 516, we have a list of even and odd properties. And I must tell you that the little table here really doesn't help me very much. As long as I remember what even means and what odd means, cosine and secant are even, everything else is odd. But then we get back to the ideas of how these are related to each other. This is on page 517. This is exactly how I was building the lists we were making. Once I know sine and cosine, I can get tangent and cotangent. But cotangent is also 1 over tangent. Secant is 1 over cosine. Cosecant is 1 over sine. What the hell are these? Well, this is the equation for our circle. What was the equation for the unit circle? X squared plus y squared equals 1. But we just wrote that cosine was x. So cosine squared is x squared. And we wrote that sine was y. So this is x squared plus y squared. It damn well better be equal to 1. This is my circle. So what about these? Well, these actually come from this one. But because that's my circle, and it's also related to the hypotenuse of my triangle, we call it the Pythagorean identity. That should be a T. Now, I see 3 versions of this on page 517. I will tell you right now, I only have this one in my head. So if somebody says to me, I want the Pythagoras that has tangent in it, I have to remember how to get tangent from sine and cosine. But that's in that same list of identities. How do I get tangent out of sine and cosine? Turn to page 517. Take a look at that list of identities. We wrote it down before. How is tangent related to sine and cosine? Which makes it sine over cosine, right? So if I want tangent, I don't need sine, I need sine over cosine. So let's take sine squared and divide it by cosine squared. But if I do it to 1, I got to do it to everything. Now I can see from some of your expressions, you're like, that's uglier. Why would you make this uglier? Well, this is sine over cosine all squared. That's tangent squared. This is cosine over cosine. Something divided by itself is 1. 1 over cosine is secant. So this is 1 squared over cosine squared. This is secant squared. And that's the next version of Pythagoras. It's written on the page, but I don't have it memorized. And people, I first did my trig class in the 80s. So I've been doing this for 40 years and I still don't have that sucker jammed into my head. I'm not going to bother. I'm going to remember this one. And if I need this one, I'll remember how to get it. If I want to go the other way and get cotangent, I say to myself, cotangent was x over y. That's cosine over sine, so I'm going to divide everything by sine. And then this is a 1. This is cotangent squared. And this is cosecant squared. Notice that I get one that's all functions and one that's all co-functions. Cotangent goes with cosecant, tangent goes with secant. The only one that mixes them is sine and cosine, because that's how we made the circle in the first place. All right. So I'm doing algebra, and I'm doing algebra about functions, and I've gotten to these properties, I can start talking about graphs. So the question is, how do I turn this unit circle into a graph? Now, I have a graphing device. That's all well and good. But I'd like to understand how those graphs are made. That is where I will pick up on Tuesday. It's going to take a couple of days to go through all the possible graphing options. Additionally, I would recommend that you read the examples in this section because they do a lot more calculation than I did. And I think that will be helpful to you. I will see you all on Tuesday. I hope you have a wonderful weekend.